Today, we continue to work on our image rendering tool using quads. Last time we ended up splitting quads one by one, which results in a somewhat dull image. And we have noticed that some quads contribute much more to the image than others. For example, this top left corner, splitting these quads won't change the image much. The colors will remain nearly the same, while at the center of the image, which is supposed to be an owl, we know that splitting these big quads would contribute and bring much more details than those quads in the corners. To achieve that effect, to start splitting quads in order of some priority, we need to introduce a data structure, in essence a priority queue, and that is exactly what we're going to do in today's episode. We're going to build a custom priority queue based on binary heap. This Wikipedia page gives you all the information that you need to build a small data structure. It is said that binary heap is a common way of implementing priority queues, but I would recommend you to watch this particular video by Pavel Mavrin, who explains it clearly in detail using lots of examples, starting with the slower implementations, eventually reaching the one that we're going to implement ourselves today. I assume that you continue watching the video, either having skimmed this information or knowing about binary heaps on your own, because I won't be explaining it in every detail, and just assume that you know about it. So if we start with our main scene, we had a queue and simply sequentially grabbed next quad, split it, put it at the end of the queue, and that's how our image rendering works right now. What we would like to do is introduce heap header file and heap C file. Let's start with our header file. And what we need to do is we need to define the structure of a heap. Our heap is quite simple. It will have an array of nodes, so something like heap node data, and we'll keep track of its length, although it's not really necessary to do so, because we can always get the length of our heap from this heap node array. But as you will see, it will be just much more simpler to directly use the length property of our heap struct. What is a heap node? Let's define that as well. Heap node will contain pointer to our quad, and it will have some sort of score, which we're going to use for prioritization. We need to include our quad, and I think there is an error in quad that we need to include pragma once, so that this header file is only included once. Now this is pretty much it about the heap. We need a few methods to work with the heap. Let's say heap init, given some heap pointer. Then we would need to push some item onto this heap. So void heap push, given some heap and given some quad. Finally, we would like to pop a value based on the score, based on the priority. And this is everything that we need. Let's grab the declarations and open our C file. Let's include our header file and start working on these methods. Heap init is as easy as setting the data to null pointer and setting the length to 0. That's all that it takes to initialize our heap. Next is heap push. So someone wants to push a quad onto the heap. Let's think what we need to do here. First of all, we need to calculate the score of this quad. We already have the average color error, and we also have the quad box area, and those properties we're going to use to calculate the quad score. Let's do that by saying that box is quad boundary box. We have a box, and we can say that, hey, there is a score which is quad average color error times, no, it wasn't actually a box, I think it was quad boundary area. So the score, there are two contributors to the score. It's pretty much the standard deviation of our color of this quad and the area. And we really want the error to be a somewhat like a main factor, but still respect the area of the quad. In this case, the area, the bigger the area, the bigger the contribution is, and we would like to lower that contribution by either taking a square root of the area or even going lower than that and saying that, hey, let's power you into this 1/4. Next is I'm used to writing the minimum heap, so I'll use minus here so that the priority of our quad to be split, the lower this value must be. And once we have our score, we can now construct our heap node. So node is actually heap node, which keeps track of the quad, and the score is the thing that we just calculated. And we need to push this heap node into our heap. That is done by array push heap data our node. Array push comes from stbds. So this node ends up being as the last element in our array, and we would like to push it up further or on top of the heap, depending like what score it has. So we cannot simply put it at the end of array and say, hey, that's it. We need to say, hey, heapify up heap given heap length -1. And we also need to say that heap length has increased because we have just pushed some data onto it. Let's see what this heapify up does. Some static void heapify up given some heap and given some index. We want to see, like, if we are at the root of our heap, at the top of our heap, if index is 0, then there is nothing more for us to do. We can simply return. But if not, then we need to see whether we need to push our node further up. And to do that, we need to check the parent, whether the parent score is bigger than ours. And if it is, then we need to swap those values. So parent is actually as easy as saying that index -1 divided by 2. Again, all these calculations you can find either on Wikipedia page or the video. The link to that will be in the description below. So we have an index of our parent, and we need to check that if heap data parent score, if the score of our parent is bigger than our score at current index, right, then we need to swap, because we want to have a minimum heap, meaning that the node with minimum score has to be at the top. So we need to do what? We need to swap those values, heap, index, and parent. And we need to proceed heapifying up from parent. So once we have swapped the nodes, index with parent, we need to check whether, again, the parent of the parent, its score, whether we need to do anything or not. What is heap swap? We need this helper method here, size TA, size TB. We need to simply say that, hey, temp node is heap data A, data B is actually A B. We're simply swapping two heap nodes in this helper methods. And this is pretty much it. And one more thing we can add here in our pushing and scoring of the quad is that when our quad becomes quite small, let's say like 4x4 or something, we don't really want to split it further, even though its error might be still indicating that, hey, the split is required here. So what we want to do is to say that, is this a leaf node? So something like box right minus box left, or box bottom minus box top. So if the squad is so small that we want to say that, hey, we will increase the score, thus reducing the priority of this particular heap node. And this is everything you need to do to push the node onto the heap. The final thing that we need to do is to pop the minimum value. We know that our heap node that we're interested in is at index 0. And how do we pop the value from our binary heap? Is we first swap it with the last value. So the last value becomes the value at the top of the heap, and then we need to heapify it down, meaning that we need to check its left and right children, and if any of those have lower score, then we need to swap the nodes. Let's see how we can do that. We can say that left is, right, this is going to be probably requiring some index. No, it's actually not index. Yeah, we need what? We need heap node. We will return the node quad. And now we need to say that, hey, let's swap them. Heap 0 and heap length -1. We reduce heap length. And we do array pop from heap. And interestingly, we can even do that a bit differently, saying that array pop returns the element it says, from data. So what we say is that we swap the top element with the last element in our heap. We reduce the heap size. We grab this last element of our array, knowing that it was at the top before and it is no longer part of the array, and we return that quad. The only thing that is left is that we need to say that, hey, we need to restructure our heap, making sure that the element that ended up at the top needs to be brought down based on its score. So we need to say heapify down index 0. Right? So our last element right here, which was at heap length -1, ended up at index 0. So static heapify down, given some heap and given some index, we can now say that, hey, we need to check children left and right. So left is index, is actually index times 2 plus 1, and the right index times 2 plus 2. So if left is, it means we don't have any left children, any left child, therefore we don't need to do any logic here at all. And we need to keep track or find which node we're gonna swap with, because if we are at the top and both left and right children have score lower than ours, we would like to swap with the one that is the lowest of those two. To achieve that, we must say, hey, smallest is actually our current index. Now, if heap data left score is smaller than heap data index score, right, we're saying that, okay, currently left has the smallest score, and if left doesn't have, we still keep smallest as index. Next, we need to check the right child, saying that if right is less than heap length, so that there is a right child, and heap data right score is less than heap data smallest score. This is very important, that here is, we're not checking with index anymore, but we're checking with the smallest, which can be either of those two. It can be either an index or it can be left. Right? So we're trying to find the lowest score amongst three nodes: our index node, our left node, and our right node. So smallest becomes right. Next thing, we need to check if smallest isn't index, right? So some node swapping must happen, because if they're the same, it means that lowest score is at our current index. What we do is, again, we simply swap using heap, using index and smallest, and then heapify down from our smallest. This is pretty much it for the heap priority queue implementation. Let's try to build it. It builds, it runs, but we have not yet integrated it. So let's do that. We are working with queue in our main, but what we are going to do is now create some heap. We will initialize it. Once it's initialized, we get the root quad. We say, let's push this root quad onto our heap. We don't need the queue index. And then for each key press, what we're gonna do is we're gonna say, hey, quad is actually, please pop from this heap. We split it. Now we have 4 smaller quads, and we need to push it back onto our heap, and it will decide which from all the current unsplit quads needs to be first, needs to be split next. Here we need to say heap, we need to say heap push, heap, and our draw image also needs to change. We need to say, hey, draw me an image based on the heap. We receive heap pointer now, and instead of using q in its length, we can say that, hey, I would like to draw everything that is currently on the heap. Heap length. So heap itself is just an array of quads which await splitting. And we can say that heap data I quad. I think this is pretty much it. Let's see what it does. So initial split is as always like this one, and then you can see that before we started sequentially it was this quad, this quad, this quad, and right now it decided that this quad has more priority than these three. You can see prioritization working, and yeah, like these two quads remain unsplit because their error is quite small compared to this owl image, right? So let's up the splitting speed. Let's say that we do 10 splits per key press. See how we end up. Right, and you can see that it actually results in a very nice looking image. Next we can try different images. Build QTA assets like tomatoes, for example. So as I said, not all the images fit perfectly, not all of them will produce nice looking result. Here these top tomatoes look pretty nice, but these smaller ones in background, they don't have enough detail for this whole picture to look nicely. This bottom tomato also, for some reason, has the error value so low that it doesn't want to split it yet. But overall, this is everything that we need for our quad renderer to be complete. The only thing that is currently missing is that if I pick a bigger picture, a bigger meaning that it doesn't fit my screen, right? You can see that this is a full screen window opened, and when I split, you can see some quads going below. And if I change the speed back to 1 and run it with this heart, you can see that, hey, there is not enough room there. We would like to fix that by adjusting the aspect ratio of the window, or pretty much even limiting the window into some area, let's say like 1024 by 1024, so that whatever the image size is, our window won't ever be bigger than 1024 pixels in width or height. Let's do that as our final change to our renderer. Now, first thing I see is that this has to be padding, right? So probably forgot, because we use padding everywhere, like in drawing image, and this padding is here in our main as well, needs to be done. So how can we do that? So first of all, when we init our context, we need to say that we will have some window width and some window height, then some image width and some image height, right? All of them are affected by our padding. Before we introduce these two params, window height, window width. Let's adjust our context init, which says it is like window width, window height, but it will also be image width and image height. So image width and image height, they affect our frame buffer. So in the frame buffer, we want to work with the full image. So we need to adjust this height. Then here, image height, image width. When we create a window, then we use the window width, window height, right? So they might be smaller than the image dimensions. Renderer doesn't use anything, and the texture also needs to be working with width and height of the image, so that when we render this texture into the window, it is automatically scaled. All right, so let's think now. Initially, we can say that window width is same as like image width plus padding, and window height is same as image height plus padding. We would like to know the aspect ratio of our image. So we might say that image, this is, because window width, because currently these values reflect the image width and height, we can use them to calculate the aspect ratio of the image. And when we find out that if window width is greater than some value, or window height is greater than some value, we can also probably extract that, right? But yeah, for now, let's keep it here. And because it is currently reflecting the image dimensions, we understand that, hey, okay, the image is too big, and we would like to have our window to be limited by the width and height of 1024. But we need to keep the same aspect ratio as our image. How do we do that? First of all, we need to check if aspect ratio is greater than 10, and greater than equal. And this means that width is bigger than height. It means that we need to limit the window width. Right? And window height becomes then, I think it's we divide by aspect ratio. Why do we divide that? It is because window width divided by window height must end up being aspect ratio. So if we take 1024 and divide by this, it will be exactly aspect ratio. And in case aspect ratio is less than 1, it means its height is bigger. We need to say that window height is 1024 and window width is then 24 times aspect ratio. And it's times here because width divided by height must be aspect ratio. And that is exactly what we get. And this is pretty much it for the aspect ratio thingy. Let's run it with our usual owl. Nothing changes, really. It's still the same. But what if we run it with our heart? You can see that before it was taking the whole screen size and even didn't fit, and right now it fits perfectly. Let's increase our split speed. Let's build it. First check it on our owl, looks nicely, and then check it on our heart, and you can see that the background has these bigger quads while the heart has smaller quads, and the water has some finer details here and there. And this pretty much concludes this project. We have built a very nice and interesting tool. We have utilized some interesting data structures, small header-only libraries. It was very interesting in my opinion. You can learn a lot from it. If you like this video and would like to see more of such projects, please do like the video, subscribe to the channel. It helps me greatly. Thank you very much, and I'll see you again. Bye.